For our projectile animation assignment, we use both Excel and GeoGebra to show our data and animation of the projectile. So, firstly, I will explain regarding the usage of Excel. The velocity of the projectile is 16.5 meter per second and the angle is 51.83 degree. Gravitational acceleration is fixed to 9.8 meter per second square. The small changes of second, which is dt, is 0.1 second. As you can see from the other table, we have time in second, Vx, Vy, x and y. Vx shows the velocity in x direction and Vy shows the velocity in y direction, while x and y will determine where to plot in the graph. Formula for Vx is velocity times sine rad angle. Same goes for Vy, but change the sign to cos. The changes in x column is initial value in x, which is 0 times with Vx times dt. Same goes to y, but using Vy value. The initial height was 1 meter from the ground, and the ball was thrown from 1 meter from the ground to the net of the basketball. For further understanding, we provide an example of animation using GeoGebra. As you can see, a basketball player is trying to throw the ball into the net of the basketball. So we have set the slider in the GeoGebra for the initial velocity to be 16.5 and for the angle to be 51.83. When we click on the fire, the animation will start and we can see the direction of the ball going into the net.
Projectile motion occurs when an object is thrown into the air at an angle. Our group used an example of a basketball player throwing a ball into a goal. It follows a curved path under the influence of gravity. The key parameters are: first, initial velocity, which is represented by u, the speed at which the object is launched. Launch angle, theta, the angle between the initial velocity and the horizontal axis. Gravity, g, is the force that pulls the object downwards. Next, we're setting up the simulation. In our GeoGebra simulation, we can adjust the launch angle, which is theta, using the slider, and we can set the initial velocity u with another slider. And the equation of motion, the position of the projectile at any time, t, is given by the parameter equation, which is u multiplied by t multiplied by cos theta. And then we can analyzing the path in the GeoGebra setup. The curve represent the projectile path, and adjusting the slider for u and theta will change the trajectory. For example, with theta 51.83 radius and the u is 16, the equation becomes 16 multiplied by t multiplied by cos 51.83. Well, what we can observe from this GeoGebra simulation is the maximum height achieved when the vertical component of velocity is 0 and the range is the horizontal distance covered by the projectile, and time of flight, the total time of the projectile stays in the air. In the simulation, adjusting the angle and initial velocity helps to understand how they influence the projectile range and height. So, conclusion, by using GeoGebra to stimulate projectile motion, we can visually and interactively understand the effect of different launch angle and velocities. This will enhance our comprehension of the fundamental principle of projectile motion.